Chapter 2, Exercise 8. Show that there is no set to which every singleton, that is, every set of the form the set containing X, belongs. Suggestion, show that from such a set we could construct a set to which every set belonged. Alright, so this is pretty much just asking us to reproduce the proof for why there is no set of all sets, and I will show you how we can do that, or how exactly that proof goes, because I don't think the book does a very good job of explaining it. It skips over a lot of explanation, and it took a while for me to grasp what is going on. So, okay, show that there's no such set to which every singleton belongs. So this kind of tells us that we should approach it by a proof by contradiction. So what I'm going to do is I'm going to say that let S be the set S equal to the set containing X such that X is a set. So, in other words, the set of all singletons. Right? Okay, so just off the bat, you can't really see a contradiction, but we're going to use one of the operations we learned in this chapter, namely the union of S, to construct a new set. Now we're going to say let A equal the union of S. And recall that this is going to be the set of X such that there exists some little s in big S where X is in little s. Right? So by construction of what S is, all these little s's, you can think of them as the containers for each one of the singletons. So really what we're saying, A is going to be equal to the set of X such that X is a set. Right? Again, the contradiction is not quite apparent. But if A really is the set of all sets, if it is a set containing every set, then it must contain this particular set. So if A contains all sets, it must contain B, where B, and I'm going to define it just as the book does, B is going to be X in A such that X is not in X. Okay? So what this means is that if B is in A, as it should be, because A contains every set possible, and B is not in B, then B is in the set of X in A such that X is not in X. And this means that B is in A and B is not in B implies that B is in B. And again, if you look at it backwards, if B is in B, then it must satisfy this condition as well, right? So we can just write the biconditional right there. Okay, which is confusing, of course. And we can further simplify this a little bit to show a more apparent and visceral contradiction. So we can simplify this to B is not in B if and only if B is in B. And now this should strike you as something that is completely um, impossible, ridiculous. Just you're breaking math in every sense of the word at this point. So yeah, this is why. Or rather, let me just. I don't want to skip ahead. Um, so this is an irreconcilable statement. There is no world. There is no possible thing you can do, at least within our formal language, to say that this is a true statement. Um, in other words, it is a contradiction. So what to do now? What do we do now? We've broken math. How do we fix it? Um, we can only conclude that B is not an A. That was like the other key component to making this contradiction happen, right? So, but then this would mean, but then B is not in A, which is equivalent to saying that B is not in the set of X such that X is a set. And thus, what do we get? Therefore, um, A equal to the set of X such that X is a set cannot exist. That is the contradiction. That is how we arrive at the fact that there is no set of all sets. As nice as that would be, that is just something that does not work, at least within our construction of what math and set theory is. So, if A doesn't exist, so A equal union of S does not exist, thus S does not exist either. That was our initial starting point for the contradiction. So that is what we conclude. Um, Therefore, there is no set to which every singleton belongs. This set does not exist. Cool. Hope that was helpful, and I will see you in the next video. Bye bye.